Welcome again to this channel. We shall proceed from where we stopped in the previous lectures, and today particularly we shall go through what we call a Gantt chart. We shall also look at process scheduling, look at what we call the preemptive and non-preemptive scheduling, and also go ahead and look at the different process scheduling algorithms. Now, I will try to make it as simple as possible as we go on with this study. Okay, so basically, to remind ourselves, in the previous lecture we had covered preemptive and non-preemptive scheduling, but basically, preemptive scheduling simply means the CPU can be taken away from a running process and given to another. It means, suppose there is a process that has higher priority than the one which is running. There's no way this process can be able to refuse. Eventually, it will be given to another process which has a higher priority, and that one will take over the CPU. For instance, we have different examples of the scheduling algorithms that fall under this. We have what we call the round robin, the shortest remaining time first, priority scheduling, and others. Now, then we have another one we call the non-preemptive scheduling. Now, usually with this, suppose a process is already running or it already has the CPU, it cannot be interfered with. For it will keep running until it has finished what it's doing, then eventually to release the CPU and give it to whosoever may have a desire to use it. So under non-preemptive scheduling, the CPU cannot be given out once a process has begun running. An example of scheduling algorithms that fall under this, we have what we call the first come, first served, the shortest job next, or the shortest job first, and the priority scheduling. Those are all different kinds of scheduling algorithms that fall under the non-preemptive scheduling. So as we look through these different scheduling algorithms, we shall encounter what we're calling a Gantt chart, because we're always required to draw it whenever we're handling some of these cases. However, a Gantt chart is just a simple graph that on the horizontal axis we have what we call the time here, which is plotted on this horizontal axis, and then we have the tasks or the processes, which are always plotted on the vertical axis. Now, usually each unit of distance along the horizontal line represents equal units of time. So we shall see how that is implemented. However, there's something to note down there. If the task follows another process or another task, then the bar follows the previous one, often each task being dependent upon the completion of another. So as we draw our Gantt chart, you'll find that upon the completion of one previous process, then another has to continue from where that one has stopped. So this is basically how the Gantt chart is basically plotted. So it will make more sense when we begin handling some cases in front here. So these are the different types of scheduling algorithms that we have. There are many others that may also fall there, but these are the ones we shall try to cover within this particular study. We have the first come, first serve, the shortest job first, the longest job first, the round robin, shortest remaining time, or the longest remaining time. So these are a few examples that we're going to cover in this particular video. So let's look at the first come, first served scheduling algorithm. Under the first come, first serve, basically, as the name suggests, it simply means that the processes are scheduled in the order they arrive. Assuming you're going to withdraw money on an what do they call them? These ATMs. Okay, when you go to the ATM and you're the first to appear there, it is you guys are following what we call the first come, first serve, because eventually as you come out, another goes in. As you come out, another goes in. So that's an example of what we call a first come, first serve scheduling algorithm. So it is very simple to implement as you see it. However, it can lead to long wait times for processes. For example, in a convoy effect, suppose the one who has gone in first has a lot of things to handle. It means he will keep these others waiting outside there until he's done with what he's doing, assuming he's depositing money, but you're using uh, that small a place that all people are waiting to use. Eventually, it can bring about long wait times in that kind of environment. So here we have a simple example that is given to us here. Usually, this is how the questions are said. They will tell you, for example, the average waiting time. Consider the following set of processes that arrive at time 0. Okay, we have process 1, process 2, and process 3, and they arrive at time 0. Then we're told if the processes arrive in the order P1, P2, P3, and are served in the first come, first served order, how would the Gantt chart look like? This is how it will look like. We shall draw this long bar, and then since process 1 came in first, because this is the order in which they arrive. Now, this is one example of what we would call a convoy effect, whereby process 1 has a burst time. The burst time is simply how long it's going to use the CPU. So you'll find that process 1 needs 24 milliseconds to use the CPU. So it means if it's the first to come there, these others, process 2 and process 3, will have to wait for 24 milliseconds until it is done with what it's doing, because there's no way it can give out the CPU, because for it is non-preemptive. Once the process has begun running, there's no way you can interfere with it until it's done with what it is doing. So process 1, when you draw the Gantt chart, we'll draw it in this manner. It begins from time 0 and runs up to 24. And so at 24, now the CPU is free. Then now process 2, which comes in next, uses the CPU for 3 milliseconds. So from 24, when you add the 3 milliseconds, it stops at exactly 27. So which means this is the time when process 2 will come in, because since it followed process 1, it is the next that follows there. Then process 3 followed process 2. So this one also has a burst time of 3, meaning it wants to use the CPU for 3 milliseconds. So eventually, from 27, you add the 3, you have your 30 milliseconds. So this is what a Gantt chart looks like if we're given in the order of first come, first serve scheduling algorithm. Let's look at another example. So with this kind of example, we're told if the processes arrive in that order and are served in that order, this is what our Gantt chart will look like. And so what will be the waiting time? If you're told to calculate the waiting time, for example, for process 1, how long did process 1 wait to be given the CPU? It only waited for 0 milliseconds, which means it never waited. As soon as it arrived at exactly 0, it began using the CPU for the next 24 milliseconds. Then how long did process 2 wait to be given the CPU? It had to wait for 24 milliseconds. It had to wait till process 1 had completed using the CPU before it could be able to be given the CPU. So its waiting time was 24 milliseconds. However, how long did process 3 wait for the CPU? It had to wait for 27 milliseconds, meaning it had to wait for process 1 and process 2 to get done before it could be given the CPU. So the average waiting time would be a sum of these 3 processes divided by 3, which would give us 17 milliseconds. So this is basically what a first come, first serve scheduling algorithm looks like. Let's look at another example here. Here now we have a different order in which these processes arrive. This time around, process 2 arrives first, process 3 follows, and then process 1 follows. And this is how the Gantt chart will look like this time around. If process 2 is the first, remember it had a burst time of 3 milliseconds. If you look at it in the previous example, so we're told that it had a burst time of 3 milliseconds, meaning it was going to use the CPU for 3 milliseconds. So which means if it arrived at time 0, it came in first. Then immediately process 3 followed, which also had a burst time of 3 milliseconds. So it began from 3 exactly when this one stopped, and then to use this time of 3 milliseconds, and it stopped at 6. Then process 1 followed with a burst time of 24 milliseconds. So from 6, it had to use 24 milliseconds, which eventually stopped at what? At 30. So this is a Gantt chart in case you're told to draw it for this kind of scenario. So the waiting time eventually would be process 1 had to wait for only 6 milliseconds because it had to wait for process 2 and process 3 to get done before it could use the CPU. So 3 plus 3 would give us 6. So it waited for 6 milliseconds. Then the waiting time for process 2, since it was the first process here, it never waited for any seconds. It only waited for 0 milliseconds, and then it was given the CPU. Then the waiting time for process 3, it means you had to wait for process 2 to get done. And since process 2 had a burst time of 3 milliseconds, it had to wait for 3 milliseconds, then it was given. And so the average waiting time would be 6 plus 0 plus 3 divided by 3, which would give us this kind of scenario here. So this is how we handle such cases. Now, let's look at some important points here to note. Once the CPU, under non-preemptive scheduling, once the CPU has been allocated to a process, that process keeps the CPU until it can release the CPU either by terminating or by requesting an input-output. So this is what happens when we have a non-preemptive form of scheduling under the first come, first serve scheduling algorithm. Let's look at a second example here. This one has something we're calling a convoy effect. We're told that suppose processes with higher burst times arrive before the process with a smaller burst times. Then smaller processes have to wait for a long time for longer processes to release the CPU, in case it is a non-preemptive form of scheduling. So here we have 5 processes which arrive with arrival time and burst times are given here. For example, you have process 1, it arrives at time 4, and process 2 arrives at time 6, process 3 arrives at time 0, process 4 arrives at time 6, process 5 arrives at time 5. And these are the burst times, meaning this is how long the CPU will be used when the process gets in. So we're told to calculate the average waiting time and the average turnaround times if we use the first come, first serve scheduling algorithm is followed. So now we're told if we're to draw the Gantt chart for this kind of diagram, there's something we note here. The first process to arrive here was process 3. If you look at the arrival time, it came at 0. So from 0, process 1 arrived, and to use the CPU for a time of 3 milliseconds. So as soon as it reached 3 milliseconds, another process was supposed to come in. But then, from 0 up to 3, the next process came at exactly 4. So from 3 to 4, there is one gap of around 1 millisecond when the CPU was idle. And that's why we have this box here. We're calling it a shaded box, which is basically the idle time. So because we expect from 3, you go to 4. But then from 3, this one stopped at exactly 3. Then that whole gap of time of 1 unit up to 4 is the time that the CPU was idle before it could be given to process 1. So process 1 comes in at exactly 4. It has a burst time of 5, which means since it is non-preemptive, it also has to use the CPU until exactly when it is done. So which means it uses the CPU from 4 when to receive the CPU at exactly 4, and then to use it for 5 milliseconds, and eventually stopped at what? At 9. So at 9, this was the second one to arrive. Then the next one to arrive would be process 5. So process 5 comes in at exactly 9 when this one stopped, when process 1 stopped. And then for it has a burst time of 4, which means you add 9 plus 4, which will give you 13. And so it stops there at 13. And then eventually process 2 comes in with a burst time of 6. In this order, 6 and this one here arrived, both of them arrived at the same time. So we're looking at one. This one here, according to this order, appears to have come a little earlier. So 6 is given a priority, and then it follows, it goes up to 17, and then finally the last process would be process 4, which completes at 19. So in that kind of order, you since it is following non-preemptive order scheduling algorithm, it means the CPU has to use the process has to use the CPU until it has completed what it's doing before it can release the resources to other processes. Now here is what we would have as a result. We have our Gantt chart here. We have our idle time here, which is a waiting time. And so the shaded box here represents the idle time. And so the turnaround time is given by the formula completion time minus the arrival time. And then the waiting time is given by the formula turnaround time minus the burst time. So from our table, we have to create other boxes here. So we shall create what we call the completion time. And so having drawn a Gantt chart, we now know that the time when process 1 completed, which is somewhere here, process 1 is here, it completed at exactly 9. So this is the completion time for process 1. By having this Gantt chart, we can just go ahead and have those values put down. And then process 2 completed at 17. We have it here. Process 3, which is this one here, completed at time 3. Process 4, which is here, completed at time 19. And then process 5 completed at time 13. So it's just a matter of copying what you have in the Gantt chart and putting it down. Then now the turnaround time is given by the formula completion time minus the arrival time. So we have the arrival time here and we have the completion time here. So by subtracting 9 minus 4, you get 5. Completion time here for process 2 is 17. 17 minus 6, you get 11, and so on and so forth. By doing that, we get our turnaround time. So then to get the average turnaround time, it means we shall have to add this plus this plus this plus 13 plus 8 divide by 5, and then we shall get our average turnaround time. So the waiting time also is given by the formula turnaround time minus the burst time. So turnaround time in this case would be what we have gotten here, which is 5 minus the waiting time, which is 5, because we also have our waiting time. How long did the turnaround time minus the burst time, sorry. So we have our turnaround time, which is 5, minus the burst time, which is 5, which is 0 here for process 1. And then for process 2, the average, the turnaround time is 11. 11 minus the burst time, which is 4, will give us 7. And so in case you're asked to calculate the average waiting time, it means you shall add the waiting time, which are here, 0 plus 7 plus 0 plus 11 plus 4, divide by 5, and that will give us the average waiting time in that kind of scenario. Okay, so this is exactly what they got here, and that's why they divided here, and so we have those units and those values given there. You try it out at your free time. So then we have another scenario given here. Assuming the arrival times and the burst times for a set of 6 processes are given in the table below. And suppose they're using the first come first serve scheduling algorithm, and there is 1 unit of overhead in scheduling the processes. Find the efficiency of the algorithm. So what we're calling the overhead here is basically some form of delay. But it seems this delay is happening for each and every process. When one process runs in, when it completes, there is an idle time before the next process comes in. So it means the keyword here is overhead, meaning each and every process has a time when it has to wait before it can be able to be given the CPU. So this is what its Gantt chart would look like. We have 0, process 1, it arrives at time 0. If they're following the first come first serve scheduling algorithm, it means process 1 has to come in first. So then before process 1 is given the CPU, there is an idle time, what we're calling an overhead here of 1 unit of time. So it means from 0 to 1 the CPU is idle. Then finally process 1 does what? Begins using the CPU. So it uses the CPU for the next 3 milliseconds. So from 1 you add 3, it will take you to 4, which is this. Then again the CPU again becomes idle for 1 unit of time, because this is happening for all the processes that are there. And that's the reason we shall need to calculate the efficiency, because there's a lot of wasted time there when the CPU is idle, when it should be doing something. But then it is doing nothing. So now process 2 comes in at 1, it comes in when process 4 is done. But then process 4, the CPU waits for one unit, and then process it comes to 5. Then from 5, process 2 begins also running, which is the CPU for 2 milliseconds, so it goes up to 7. Then from 7 again, the CPU becomes idle for 1 unit, which goes up to 8. Then from 8, process 3 comes in with a burst time of 1, so which means it uses CPU up to 9. Then again, the CPU becomes idle, and so on and so forth. So by doing this, we have our Gantt chart of this given scenario. So to calculate the efficiency, we shall need to find out the wasted time, or what we call the useless time. And so in this case, we have 6 processes, and all of them have a unit of 1 second, which is wasted before they're given the CPU. And so that's why we have 6 times that unit of wasted time, which will give us 6 units. We can just say 1 plus 1 plus 1 plus 1, 6 times, which will give you eventually the 6 units of time, which is wasted. So now, the total time that we have overall is 23. That's in addition to all these other wasted times that we have there. So which means the total, the useful time that the CPU is able to use would be the total time minus the wasted time, which is 6, would give us 17 units, which means literally this whole work should have been done within 17 milliseconds. And so because of this added 6 units of time, which was idle, we had to spend 23 milliseconds. So the efficiency would be the useful time over the total time. The useful time is 17 over the total time, which is 23, which eventually gives us 73.91% of efficiency. Okay, so let's have the second scheduling algorithm. Now this one we're calling it the shortest job first scheduling algorithm. Sometimes it's also called the shortest job next. So basically this one is a scheduling process that selects the waiting process with the smallest execution time, or the smallest burst time. So it will look at the processes that are available, and then it will determine that, oh, this one has the smallest burst time. It should be given the CPU first before others can be given. However, in some cases, the exact burst time of the process may not be known in advance. So in such scenarios, an estimation formula is used to predict the next burst time based on the previous burst times. So let's look at a few examples here on how this is done. Some of the characteristics of shortest job first. It has an advantage of having a minimum average waiting time among all the operating systems, because usually the one with the lowest burst time will come in first. So because that one comes in first, there is literally a very small waiting time that is available, because all processes run in faster as compared to first come first serve, whereby in case a long process comes in first, it means others have to wait for a long time, which is a very big problem. So it's associated with each task as a unit of time to complete, and it may cause starvation if shorter processes keep coming. So it also has a challenge. If processes that have shorter burst times keep coming, it can bring about what we call starvation. Others will wait for a very long time, though they may have come in early, but in case others of shorter burst times come in, eventually they have to wait, which becomes a problem to them. Let's look at this example here. Consider a set of processes with the length of the CPU burst given in milliseconds. We have process 1, process 2, 3, and 4. Now, this example we're given here, we're told is non-preemptive. With this being non-preemptive, it means the CPU, once a process has entered the CPU, it cannot be allocated to another process until it is done with what it is doing. So, when we look at this process, which one has the lowest burst time? Because we're looking at shortest job first, which means the burst time determines how long the process is going to use the CPU. So you realize that process 4 has the lowest burst time. So to draw the Gantt chart, we shall begin. We shall draw, have this square of hours here. Then we say from 0 to 3, process 4 will utilize the CPU. Okay, so it's using the CPU for 3 milliseconds and eventually stops at 3. And since it is non-preemptive, it has to finish what it is doing before it can be given to the CPU can be given to another process. So then the next one to follow here seems to be process 1, because 6, 8, and 7 is 6, which is lower. So process 1 then follows, which has a burst time of 6, which means it will also use the CPU for 6 units of time. So it means from 3, when you add 6, it will give you 9 exactly here. So this one also gets done. Then process 3 will follow with 7. From 9, it will use process 3 will use 7 units of time, which will take it up to 16. Then it will stop. Then eventually the last process will come in, which is process 2, which will come in from 16 and will use 8 units of time, which means it will stop at 24. So realize this is shortest job first scheduling algorithm. They should not confuse you, because in the first come first serve, the order of arrival was considered, and if it was non-preemptive, it means that order had to be followed until all the processes are done. But this time around, though we're having non-preemptive, this is the shortest job first. It means we shall look at the burst time specifically. Which one has the lowest time it spends in the CPU is given the first priority, and that's basically how this one is done. So to calculate the waiting time, process 1 had to wait for 3 milliseconds before it could be given. It is right here. So it means it got the CPU as soon as process 4 was done, which means it waited for 3 milliseconds. And then process 2, this one had to wait for 16 milliseconds. You had to wait for process 4, process 1, and process 3 to get done. So which means you have to wait for 16 milliseconds. And then process 3 had to wait for 9 milliseconds. It had to wait for process 4 and 1 to get done before it could be given the CPU. And then process 2, which is the last one, had to wait for 16, and so on and so forth. So now, to get average waiting time, we add up these waiting times, divide by the number, which is 4, which is the number of processes, which will give us exactly 7 milliseconds. Okay, so that is an example of a shortest job first scheduling algorithm. Now we have another scenario here. We are told to consider the following processes with the arrival time and the length of CPU burst given in milliseconds. However, the scheduling algorithm used is preemptive, shortest remaining time first. It is preemptive, meaning this time around, even though a process has begun running, as soon as another process with a lower burst time comes in, it means that process has to be exempted. It has to stop what it's doing, and then this one with the lowest burst time will come in and will begin using the CPU. So unlike the first example, whereby it was basically non-preemptive, it means everything had to run as usual, but this time around it is preemptive. And so if a second process comes in and it has a lower burst time, it will be considered unlike the first one. So we're told the average turnaround time of this process is dash millimeters, which means that given us a scenario, and after calculating all the turnaround time, we're supposed to see which of these answers is the correct one. So what we do, we begin by drawing our Gantt chart in this case. And so how did you arrive to this? We first draw our row, this long row of ours here, and then we realize that the arrival time for process 1 was 0. So we'll put our 0 here. And so process 1 began running at exactly 0. And so no other process came in at time 0 except process 1. So which means from process 1, it had a burst time of 10 units, meaning it was supposed to use the CPU for 10 units of time. However, at exactly 3 seconds or milliseconds or 3 units of time. When it had just run, when it had just moved for 3, when it had used the CPU for only 3 units of time, process 2 arrived. So which means it had only used, after of having used the 3, it means it had stopped at what? Its buffer time had remained with, it needed more 7 units of time to complete what it was doing. So at exactly 3, process 2 came in. So when process 2 came in, process 1 had remained with 7 units of time waiting. So at time 2, process 2 comes at exactly 3. Process 3 and 4 had not yet arrived. These ones are not, which means assuming it was you had gone to a bank and you have gone to those ATMs to withdraw money. At time 0 exactly, there was only one person there. There was only process 1 which was there, and so it used exactly 3 units of time when process 2 came in, which had a lower burst time compared to process 1. You get the point? So this one had a lower burst time, which was 6 compared to process 1. So eventually it had to be given the CPU. So it also used the CPU for from 3. It uses the CPU up to 7, up to the 7th time when this one arrived. So which means it had used 4 units of its time. Of the 6, it had used 4 of them, and so it remained with the 2. So which means at exactly 7, if you realize critically now, at exactly time 7, process 3 came in. Now process 3 only needed the CPU for only 1 unit of time. So it used its time from 7 to 8, which was 1 unit of time. And then at exactly 8, when process 7 complete its running time, this is what happened. At exactly 8, process 4 was supposed to come in. But then, since we're looking at the shortest job first, it looked at all the burst times of the different processes. This one came in at 8, but it found these others were already there waiting, and even amongst them there were those that had lower burst times compared to it. Though it had a burst time of 3, process 7 was done, okay, process 3 was done, but process 2 had a burst time of 2 compared to it, which had a burst time of 3 when for it arrived. So because it arrived at time 8 and had a burst time of 3, and process 2 had a burst time of 2, process 2 had to come back again and use the CPU. So process 2 began using the CPU at exactly 8 when process 3 stopped, and then it finished now its time. It used its time up to 10, and so it also got complete. So when it got complete, we're now left with process 4, which has a burst time of 3, and process 1, which has a burst time of 7. And so when you compare the burst times, you realize that now process 4 now has a burst time which is lower than process 1. So process 4 now comes in here, uses this burst time of 3 units of time, which stops at exactly 13, and then eventually process 1 now comes in and also uses the CPU for the remaining time, which is 7, and then finishes exactly at 20. So this is basically how the preemptive scheduling under shortest job first is able to work. So here you have to notice that you consider first of all the arrival times, but as you consider the arrival times, you keep on comparing the burst times to see which one has the lowest and which one should be given the CPU as compared to the other. So because of that, we now go ahead and we calculate now the turnaround time. We can now write out from our formula. We know that turnaround time is given by the completion time minus the arrival time. So when we look at process 1, which is here, it completed time 20. At 20 minus the arrival time when it arrived was basically time 0, so it finished. It has 20 milliseconds. Then process 2, which is somewhere here, completed at time 10, which is this, minus now its arrival time. Arrival time, which was basically 3, and so you get 7, and then the rest. So by adding them up, you divide by the total number of the processor, which is 4, you get our answer, which is 8.21, and that's why it was this alternative A, which was the correct answer according to this kind of scenario. Okay, Now let's look at another second example. Now also here we're told an operating system uses shortest remaining time first scheduling algorithm for preemptive scheduling of processes. We said preemptive scheduling, it means processes can release the CPU and give it to others which have higher priority as compared to them. And so because of that, it means they will keep on switching and on until the processes are done. So consider the following set of processes with their arrival times and the CPU burst times in milliseconds. Process 1 arrives at time 0, it has a burst time of 12, and so on and so forth. The average waiting time in milliseconds of the process is dash. So we shall find out which of these answers is the correct one. So, given this process, process 1 arrives at time 0, it means we shall have to begin with that one first. It arrives at time 0. So it means at time 2, at time 0, process 2, process 3, and process 4 were nowhere to be seen. So which eventually, process 1 had to begin running. Okay. However, it had just used the CPU for 2 units of time, which means here it means it is remaining with 10. Having used 2 units of time, it was remaining with 10 here. Process 2 arrived. You get the point? So when process 2 arrived, for it, it used the CPU. This is process 2 arrives at this time. It uses the CPU for, first of all, for one unit of time. 1 unit of time, which means it's remaining with 3 here. Okay? 1 unit of time is remaining with 3 there. Then, this one was supposed to come in at exactly 3. But then, this one has used 1 unit of time and so it's remaining with 3, meaning it is now, when you compare the burst times, this one has 3, this one has 10, okay? This one has 6 and this one has 5. It means this one has to continue running. It still has the lowest burst time. So, process 2 eventually uses all this burst time of 4 units of time until it stops at what? At 6. Now, at exactly 6, when it finishes up, process 3 with this arrival time of 3. Now remember, this one is done. This one is now completed. We're having now 5, 6, and 12. But this one here had arrived earlier on. It had arrived at time 3, which means the only process which is now supposed to come in and use the CPU should have been is basically process 3, because process 8 is still way forward, is still in front. But remember, this one has completed at time what? At time 6. So which means at time 3, process 3 eventually comes in immediately after this one has come in. So it uses the CPU. First of all, it uses the CPU for 2 units of time. Remember, it has 6 of them. When it uses 2 units of time, I mean from 3, from this time, it uses the CPU until it finishes its burst time of whereby it stops at exactly 12, because it had 6 and then it began at 6. So when it ran for maybe the first 3 units, 5 units of time. It remained with 1 here. So which means it reached the 8th time when this one was supposed to, when process 4 was supposed to arrive. But then, since it was only having a burst time of 1, it was the lowest there. So it had to finish up until 12. Then, when it finished there until 12, we're now left with process 4, which has 5, and process 12, and process 1, which has 10. Okay, which has 10 here. Now, process 4 with a lower burst time of 5 has to use the CPU until it finishes in 17. So when it finishes in 17, now process 1 comes in, which has a burst time of 10 remaining here. Because it had also come in the first time, so it remains with 10 here. And so 10 plus 17 will give us 27 when process 1 finally finishes its use of the CPU. So, as usual, we calculate now the waiting time for process 1, which finished at 27. So it means it is the waiting time would be it's arrival time minus it's completion time minus the arrival time, which eventually will give us 15. And so you do the same for this. It's arrival time, completion time, which is 2 for process what is this? This is process 2. Process 2 finishes at 6. Its completion time minus arrival time, which eventually will give us 0 here. What is this? 2 minus 0. You get again 0. This is not correct. 2 minus 0 minus 2. Okay. So you subtract that, and then eventually we're able to get the average waiting time, which eventually will give us all the things. So the waiting time is equal to total time minus the number of milliseconds processes executed minus the arrival time. So this is how they got the waiting time in this kind of scenario, which eventually gave us that kind of answer there, which would be option C in that given example. So you can try that out at your free time and see how this magic come about. So in real implementation, we usually input a number of processes and their burst times, and we consider whether it is non-preemptive or preemptive. So if it is preemptive, it means they can be able to switch as the processes are running. If it is non-preemptive, it means they cannot switch as the processes are running. So if that is so, we'll now go ahead and sort the process by the burst time. If they're the same, we use the arrival order. Assuming you have a case whereby the burst times are the same, it means we shall consider the arrival order of such a scenario. So we usually start with processes having the shortest burst time, and then we'll go ahead and calculate the completion time, which is equal to the start time minus the burst time plus the burst time, calculate the turnaround time, repeat all the processes, and so on and so forth. Now this basically helps us to see how we can implement the shortest time, the shortest job first scheduling algorithm. So advantage of shortest job first, it's better than the first come, as it reduces the average waiting time in that scenario, because here we don't have to wait long, because the one with the lowest time is one who begins first. So another advantage is that it's generally used for long-term scheduling. It's very good for scheduling in long scenarios. It is suitable for the jobs running in batches where runtimes are already known. So this one is very good in such scenarios. Disadvantages, this one may cause very long turn around times of starvation. It can cause very long turn around times for starvation, or completion time must be known earlier in order to process the things quite better. But in case they're not known, sometimes it is very hard to calculate them. So many times it becomes complicated to predict the length of the upcoming CPU request. Okay, let's look at round robin. Round robin is basically a scheduling algorithm also. For it, the method is used by operating systems to manage executing time of multiple processes that are competing for the CPU attention. It is called round robin because the system rotates through all the processes, allocating each of them a fixed time slice or quantum, regardless of their priority. So it wants to resemble the shortest job first. However, in this case, all processes are allocated a certain amount of time. For example, each person will be allocated, you must use 5 units of time. Another one also uses 5 units of time. Then after all the units of time are done, the second round comes in. In case you still have, you also go in until you complete your processes. So this one is what we call the round robin. So the primary goal of this scheduling method is to ensure that all processes are given an equal opportunity to execute, promoting fairness among the tasks that are given. So this is the advantage of round robin. So the processes, for example, here the processes arrival. Here processes enter the system and are placed in a queue. And then what happens next? There's time allocation. Each process is given a certain quantum of time or a certain amount of time, which we're calling the quantum. Now the process uses the CPU for the allocated time. If it still has other needs to use the CPU, it will have to wait until the second round comes in before it can be done. So rotation then comes in. If the process completes within the time, it leaves the system. However, if not, it goes back to the end of the queue and waits for its turn to come, then repetition will come in. So the CPU continues to cycle through the queue until all the processes are completed. So this is basically how the round robin is able to operate. Advantages of round robin: it brings about fairness. It's quite simpler. Uh, it allows for responsiveness. Disadvantages: it can bring about overhead. Switching between processes can lead to high overhead, especially if the quantum is too small. And also there's underutilization. If the quantum is too large, it can cause the CPU to feel unresponsive as it waits for a process to finish its time. Because suppose you're given a process which is supposed to run for maybe 3 milliseconds, you're given it a quantum of 5 units of time, which means there's a lot of wasted time there. So underutilization of the CPU because of such kind of a scenario. We have another thing called the priority scheduling. Here, processes are scheduled based on priority levels. High priority processes are scheduled before the low priority one. So here each process is assigned a priority value based on the criteria such as the memory requirements, the time requirements, other resources, or the ratio of average input to average CPU burst time. So the process with the highest priority is selected for execution first. If there are multiple processes sharing the same priority, they are scheduled in the order they arrive. So which means priority scheduling may want to operate like shortest job first. However, with shortest job first, we consider the one with the lowest burst time. But then with the priority scheduling, there is a level of priority that is considered. So which means the highest priority will be executed first. However, in a case whereby they have the same priority, the one that came in first will be considered. So which means they will follow the first come first serve first, then eventually again they will go back to that kind of order. So this is basically what priority scheduling is all about. So priority scheduling can be implemented in two ways. It can also be non-preemptive or preemptive. If it is non-preemptive, the CPU is not taken away from the running process. Even if the high priority process arrives, the current running process will be completed first. So it means that one which is a high priority must have to wait until the currently running process is done. However, if it is preemptive, the CPU can be taken away from the currently running process as soon as a new process with a high priority arrives in the CPU. So a low priority process is running and a high priority process arrives, the CPU immediately switches to the high priority process. So that's exactly what priority scheduling is all about. Then we have another one called the multi-level queue scheduling. Now here, processes are divided into different queues based on their priority and type, with the different scheduling algorithms applying to each queue. The disadvantages of this multi-level queue: it provides flexibility. Advantages: provides flexibility and control over different types of processes. The disadvantage is it is complex to implement and to manage. So these are basically the different types of scheduling algorithms that we have as far as this particular course is concerned. There are others that are also there for your own research. You'll have to try them out. But for now, we shall stop here in these scheduling algorithms. Till then, I remain yours. Bye-bye.